Okay, I'm going to go through this section 2.1. I've left out a lot of the slides. And a lot of it you're going to have to read by yourself because I think a lot of it is self-explanatory. So, sets, collection of stuff, elements. These are things that belong in a set. So here we have the 4 seasons. There's 4 elements in the set. The roster method is the easiest way to list things. So notice here's a big key. So we've got the roster method for the set S, which is the set of the seasons. It doesn't matter about the order. So the order we list them doesn't matter. These are the same sets. Okay, so here's an example. Set of states in the US that border the Pacific Ocean. I think I wouldn't have got all these because I probably would have forgot Alaska and Hawaii. But notice we just listed them by name, and that's an easy way to do sets. Just put them in a roster, just be careful. This, it's the brackets that make a set. It's not parentheses. And it's not those, and these are, I'm gonna have to come back to that. I can't think of the word. These may not be brackets. Sorry about that. Anyway, it's a little squiggly things. Oh, too funny. Okay. I'll think of it probably when I'm done doing this. Okay, roster method, days of the week. Again, we could have done them in any order. Okay, so here you can go from roster method to describing them in words. For instance, I could give you this set. And you could say, oh, that's the first 4 even numbers. Okay, there are some sets here that I really want you to know. I want you to know natural numbers. Notice those are counting numbers. We probably talked about these before. Then when you add 0, you get the whole numbers. Then when you add these negatives, the opposites of those, so the opposite of the naturals, you get integers. Rational numbers, this is really not the definition. Rational numbers are ratios of 2 integers. Meaning things like 4/7, -13 halves. So really fractions. Okay, roster method. Set of natural numbers less than 5. I think the natural numbers, I start with 0 and I go, no way, that's not a natural. So less than 5, 1, 2, 3, 4. Let's call that set A. B is this. Let's see, we solved that. X equals -6. So set B only has 1 element in it. It's -6. And this last one, set of negative integers greater than -4. Let's see, negative integer would be -3, that's greater than -4, -2, -1. Then I'm done with the negative integers, and there's that roster. Okay, well defined, if you know something's in the set or not. So I actually like their example is something that's not well defined. If you think of the set of great songs, we could argue about it. We don't know what's in the set. We don't know what's out of the set. Something happened when I moved this PowerPoint around. This is not the symbol. The symbol is 4 is an element of n. So 4 is an element of natural numbers. -3 is not an element of n. So this is our element of sign. So that's not an element. Okay, true or false? Let's see. Is 4 an element of this set? Well, there's 4, so that's true. Is -5 an element of the naturals? Well, let's see. Naturals are 1, 2, 3. No, that's false. It's not an element. 1/2 is not an element of the integers. That's true because there are no fractions in the integers. Set of nice cars. Is that a well-defined set? No. So this is false. We don't know what's in the set of we don't know what's in the set of nice cars. Too much argument about it. Again, symbol screwed up. This is the null set or the empty set. Set with nothing in it. It's actually an important set, believe it or not. And now we're going to learn about set builder notation. Before I do that, I'll ask you a question. Give me the set of negative numbers in W, the whole numbers. Well, there are no negative numbers in whole numbers, so you would say it's the empty set. Or you would give me the answer like that. Braces, that's what those are called. Brackets are these things. Okay, we're going to play with this a bit because this is different. But it's a nice short notation that collapses a whole bunch of words, and you're going to have to play with this. So I'm going to write this and talk about it. Okay, so the set of all elements X such that X is an element of the natural numbers, so I know where I'm taking my X's from. And X is greater than 7. If I did that in the roster method, that would be 8, 9, 10, on up to infinity. But I can't list all those really. So we do the set builder notation. Okay, set of integers greater than -3. Let's call that set A. The set of elements X such that X is an element of integers and X is greater than -3. So I'll expect you to be able to go back and forth. Like if I gave you this, could you list these out in the roster method? Let's see, integers greater than -3. -2, -1, 0, 1, 2, 3, and so on. Okay, let's do set B. Set of whole numbers less than 1,000. Okay, so set B, elements X, such that X is an element of the whole numbers, and X is less than 1,000. This is not so easy to write in roster form. I could do whole numbers, I could do this, and then I could just end them with that, up to 999, and then the ellipses skip everything in between, but they are there. Okay, if you can count stuff, stuff is finite. If you can count stuff, the cardinal numbers, how many things you have. So we talk about the cardinal number or the cardinality of a set. Here, A has 4 elements, so the cardinality of A is 4. If I did this, letters of alphabet, oops. Well, the cardinality of B would be 26. There's 26 elements in B, and we can count them all. So it's finite. Okay, cardinality. Well, cardinality of J, I can do that one, that's 2. Cardinality of S, well, these are all natural numbers. We're missing 1 and 2, so it's 31, subtract 2, so that's 29. Cardinality of T is really just 3 because the 3 was listed twice and we only list one element once when we do a set. Okay, equal. Right here. A and B have to have exactly the same elements. So if this was A, this was B, we would say, yeah, A is equal to B because they contain the same 3 elements. Equivalent is not as powerful as equal. It's if they have the same number of elements. So notice here, in this case, the cardinality of A is 3, same with B. So in this case, A is also equivalent to B, but equal is a stronger statement. So last slide. Well, there's no way these are equal. And I hate how they don't give these things names. So I'm going to name this A and N for letters and numbers. A is certainly not equal to N. They don't have the same members, but cardinality of A is 5. Cardinality of N is 5. So A is equivalent to N. They have the same cardinality. Here, if you had A and B, well, look at this. A is not equivalent to B because there's 3 elements in A, 4 in B. So if you're not equivalent, you can't be equal. So this one is neither. That's it. Come on, go back. You do this to me all the time.